First of all, I want to thank the organizers for this very nice workshop in a place I've never been to before. And it's been wonderful to hear about all the exciting results in this field in the past few days. So today I just, hopefully not talk too long because everybody is tired, etc. Just present the work that I've been doing with my student, Konstantin, and a lot of master students and more junior PhD students in our lab, and which is about understanding the effect of the strength of an inductive bias on whether interpolation is harmless or not. So I'll explain in a second what I mean by inductive bias. First of all, we've heard a lot about how neural networks have defied classical wisdom in the sense of double descent, etc. So I'll only quickly go through this first few slides. So this is the slide I usually use for my Introduction to ML course, where of course if you use a high degree polynomial without regularization, you will highly overfit on noisy data points. And if you regularize with, for example, a rich penalty, then you will get a much closer function to the original red function. Okay, so regularization helps in low-dimensional settings. That has been well understood. But there's been this new kind of story, which is for neural networks, this is not quite the case. So this is an experiment done by Nakaran et al. So basically, they looked at noisy C410 samples. So it's important that they add artificial label noise because you don't know whether C410 is actually a noisy data set, or maybe there's almost, or very little noise. So let's say we have noise, then there could be a problem of overfitting, right? So now what is the x-axis, right? So double descent always needs an x-axis. In this case, overparameterization is reflected by this width parameter of a ResNet. So we have a fixed depth ResNet, and we vary the width. On the y-axis, we have the test error. And all the different curves are the test errors of trained neural networks at a particular epoch. Right? So the blue one is if we take each of these neural networks with different width, we train it until convergence and look at the test error. Right? So the blue one is the one that is trained until convergence, and then there are some intermediate epochs. Right? So what you see here is that for one, that we have this double descent phenomenon, that for the blue curve only, we see it goes down, it goes up, and it goes down again. So this is the one part of the double descent, is that there is a second descent after the first one. Okay, so this has been a bit puzzling, but by now kind of well understood, as we saw in previous talks this week. And then there's a second phenomenon if we focus now on the very far end, and we not only look at the blue one, but also at the red curve. The red curve is basically an oracle curve, so you look at for each width parameter, which is the epoch that gives you the best test error. So if you're at the very far end, what you see is the blue and the red curve are the same, which means optimal early stopping does not help generalization. But if you're close to the interpolation peak, of course it helps. So as we have seen in many talks, regularization gets rid of the peak. Okay, so we have, for large models, we have that interpolation is harmless. So we have these two phenomena. And the other phenomenon is, of course, that generalization is still good. So basically what we want to understand is for what kind of interpolators do all three of these properties hold. So for one, we have the second descent, which is overparameterization helps interpolators. Then we have harmless interpolation and good generalization all at the same time. And so what people have usually studied so far is basically we fix one particular interpolator, for example, minimum L2-1 interpolators, and then we look at when can it generalize well, when do we have benign overfitting, meaning that we have consistency as DNN go to infinity for linear models, or when do we even have good rates. And so this usually depends on some sort of spike covariance model where we have effectively low-dimensional covariance. So yeah, also the first point is quite well understood. We've seen these in previous talks yesterday. And so I will focus on the 2 and 3 and when these actually can hold. So we'll see in a second what I mean by this good generalization. So it goes beyond consistency, and it basically is looking at actual high-dimensional distributions in the covariate space, meaning not spike covariances, but isotropic ones. Okay, so we have a lot of interpolation possibilities, right? So in high-dimensional models, over-parameterized models, we can have infinitely many interpolators. So the question is, what kind of interpolators can satisfy all these three properties? So a lot of literature we've also heard this week is focused on, if we take an optimization algorithm that is minimizing some loss, such as gradient descent-based methods, then we have some implicit bias towards a certain interpolator. So this is what's called implicit bias. And so what I'll use a lot in the rest of the talk is the concept of structural or inductive bias. And what we mean by that is, given a certain interpolator, for example, minimum something norm, this norm has, or this interpolator has a structural or inductive bias towards a certain structure, right? An inductive bias towards a structure such as sparsity invariance, certain types of invariances, or small filter sizes. Okay, so basically, we are focusing on, given some interpolator, looking at its inductive bias towards a certain structure. So we're not looking at the left side, only on the right side. So we're not looking at the optimization algorithm, etc. So we're just looking at fixed and comparing different types of interpolators with different strengths of inductive bias here. So, okay. So before I go on and give an example for inductive bias, so we will focus on the case where, again, the covariates are high-dimensional in the sense like isotropic, so we don't really have a spike covariance model. So this is a big difference compared to previous works. And in this case, right, good generalization can only happen if you have some sort of clue where to search, right? So that's the whole idea behind regularization towards, for example, in the L1 case, in the sparse ground truth case, you want to have regularization towards sparse ground truth, right? So if you have really an over-parameterized model and your covariates are really high-dimensional diverse, you really need some sort of clue. Okay, and so you need this inductive bias if you're over-parameterized and you have isotropic covariates. And so the key mechanism for when all of these three holds is now the strength of this inductive bias. Right. So how strongly am I encouraging my interpolator to have this simple structure? So this is going to be the key knob that we will turn, and that is different to compared to previous results, which usually look at the knob of over-parameterization. We look at fixed over-parameterization and check how the strength of the inductive bias is influencing all these properties, in particular harmless interpolation. Okay, so this is the main story of this talk, that we'll focus on the strength of inductive bias. Okay, so again, so what is the role? So I'm going to actually tell you what we observe first, and then I'll give some concrete results. So the story, the role of the inductive bias is really simple to just illustrate with a very cartoonish picture. So we have these two regimes, right? So on the left side, the x-axis here is over-parameterization, the standard one. On the left side, we have under-parameterization, right? So we cannot fit data perfectly. Training error is above 0. And then we have beyond the interpolation threshold, we have the second descent, and we can achieve 0 training error. So now we add this essentially second dimension to the over-parameterization, which is the strength of inductive bias. So now let's look at classically how we think about strength of inductive bias. So classically in the left regime, right, so say we're kind of close to interpolation, but not quite there yet, or generally what the kind of intuition that we have, if we allow the inductive bias to prevent interpolation, such as in lasso, right, so we add a regularization penalty, then basically our intuition is that the bias increases and the variance decreases, right? So we're shrinking the amount of flexibility to fit the data. That means we potentially increase the bias and decrease the variance because of a smaller space to search over. Very important here, okay, so here is towards the left side is increasing inductive bias via the regularization parameter. If we increase lambda, variance drops and bias increases. But at the same time, it's important to note that we're allowing the training error to go up as well, right? So we're sacrificing fit to gain some structure, or some simplicity of structure. So this is the classical view of inductive bias strength. It kind of helps to some extent, in particular if it's not too large. So it's somewhere in between, and then regularization can do well. We get minimax optimal rates, etc. So now we're in the second regime where training error is always 0. So how is the effect of the strength of inductive bias in this case? So here the picture is actually the opposite. Okay, so the difference here is, again, we are increasing the inductive bias via some structural terms. And in the case of linear regression, we would be varying the p-norm between 2 towards 1. Right, so p equal to 1 has a strong inductive bias towards sparse solution. P equals to 2 has essentially no inductive bias towards sparse solutions. This is what you can imagine the inductive bias is doing, or like turning the knob in this case would mean. And very importantly, the training error is always 0. Right, so we're in the interpolating regime. In that regime, the strength of inductive bias actually is varying bias and varies the opposite way. Okay, so as we increase inductive bias, the variance increases and the bias decreases. Now, of course, this is only true if the inductive bias aligns with the optimal parameters or the optimal solution. But let's assume that's the case, right? So we know our solution is sparse, for example. So now the question is, should I choose p equal to 1 or should I choose p equal to 2? Of course, p equal to 2 is probably not true, but not good, but what about p equal to 1? And we see actually p equal to 1 is also not good because the variance is going to be high. So kind of the takeaway here is, if you're forced to fit noise, right, having a smaller or less flexible set, which is the set of sparse solutions, actually increases your variance. Okay, so if you think about, I don't know if I have a slide on this in the end, but if you think about it like this, essentially, previously, right? So previously, you vary your size of the set, and by varying those, the size, you basically say, okay, don't fit the data perfectly, you're going to be closer to your ground truth. In this case, you're saying, still fit the data perfectly, but with a much smaller set. What this means is, for example, if you think of the linear case, and you think of W star is equal to 0, so you have to fit noise when you interpolate, right? But if you have to fit noise with sparse solutions, the norms of these vectors are going to be larger. They're going to be larger, and hence, your variance, which is essentially the norm of the W hat, is also going to be larger. Whereas if you basically say, I'm allowing all directions, then the vectors that if you're forced to fit noise, then you can choose a vector that kind of uses all directions, right? So you don't you allow more flexibility, and hence you can find a vector with smaller norm. And that is the whole idea that essentially if you're forced to fit noise, a smaller set can actually blow up your variance. So it has the opposite effect than for the case where you allow to sacrifice data fit. So this is basically the takeaway of this talk. The rest of it is just going to be trying to understand, how well can you do in the middle between p equal to 2 and p equal to 1. And we also are going to see some results for p equal to 1 that basically prove that your rates are still very bad, even though you can get consistency. Okay, so I always mentioned these linear examples because that's easiest to think about. A lot of people are familiar with sparsity. So in the first part, I'll just show you some results for sparse ground truth. and for p between 1 and 2. But more interesting, I find, is the second part, hopefully can get to, which is for nonlinear models, where the structure is going to be the filter size of convolutional models. We have both theory for kernel interpolators, and we have experiments for neural networks. And then we also study this kind of bias-variance trade-off for rotational invariance for neural networks in some controlled experiments. Okay, so let's start with linear interpolators first. Linear regression setting, we've seen a lot already this week. So we look at Gaussian covariates isotropic. It's different than most other works that achieve consistency for spike covariances. And we have Gaussian noise. And importantly here is that we can only prove this for Gaussian covariates. Essentially, all of the results crucially rely on those, and we and a lot of other experts don't know yet how to extend this beyond. So this is an open question, but for Gaussians, we can show what I'm going to talk about next. And then we assume for this talk that W star is just 1, 0, 0, or just one sparse, but our results hold for all of S sparse ground truth, or S that is on the order of n over log d. And so then the degree of overparameterization, instead of looking at the regime where d is of the order n, which we've seen a lot, right? So we saw a lot of asymptotic results there. We'll focus on the regime where d is of the order n to the beta, where you can actually achieve consistency. So when beta is bigger 1, d is bigger than n, and so you can interpolate, right? So as beta grows, we have more and more overparameterization. So the interpolators will compare our minimum LP norm interpolators, subject to y equal to xw, the interpolation constraint. And because we want to look at harmless interpolation, we also compare this with regularized estimators and their rates, in particular the lasso. Okay. And of course, I don't need to mention that minimal P norms are somewhat natural to study because of implicit bias results, in particular for classification, but also for some P for regression. In particular, P equal to 2, but yeah. We also have results for classification for anything I'm talking about today, basically logistic regression, or just say hard margin SVM, and for hard LP margin SVMs, but I won't talk about them, so otherwise it become too crowded. And the performance metric for regression here, there's the prediction error, which in the case of isotropic covariates is just the estimation error W hat minus W star L2 norm. Okay, so yeah, so the right-hand side on this 3-plot slide before was basically varying the inductive bias strength, right? And I said for linear models, this just means varying P equal to 2 towards P equal to 1, between 1 and 2, that's what we study. This is our knob. P equal to 1 has strong inductive bias to sparsity, and P equal to 2 has no inductive bias towards sparsity. Previous work has focused on P equal to 2. And so today we will populate the picture beyond P equal to 2. But before we go there, I just want to briefly recap what's already known for P equal to 2. For P equal to 2, you look at the minimum L2 norm interpolator and the ridge regression estimate. You can compare these two. And what is nice about P equal to 2 is that you have a closed form solution. You can use random matrix theory pretty directly. That's also one reason people have studied this extensively. What we see for P equal to 2, these are just some very simple experiments for isotropic covariates, is that for D over n bigger than 1, we see both the second descent and we see harmless interpolation. Right? Harmless interpolation means the optimally regularized one and the interpolating estimator have the same MSE. In particular, if you have very high overparameterization, harmless interpolation holds. Okay, and the reason is that as you increase d over n, the variance drops. So if you remember Misha's result n over d, right? So as you increase d over n, this lower bound drops, and the lower bound is essentially coming from the variance in this case. So here, variance drops. So if the variance is really low, regularization is not going to help you anymore. So this is why you have harmless interpolation. So you can basically, the fact that variance decreases, you have implicit regularization, explains both second descent and harmless interpolation for p equal to 2. Okay, so we have these two, but we wanted good generalization as well. And that's the problem with L2, is that the Bayes error is somewhere there, and because the bias is increasing, right, so you really have no clue where to search, the risk is also very high, much higher than the Bayes error and what you could get if you used lasso, for example. And so for isotropic Gaussians, you have a very high bias and hence a very bad generalization and no consistency. Okay, so this setting is not satisfactory, and that's why we looked at p between 1 and 2. Okay, so here, p equal to 2, as I just pointed out, for high overpolarization, variance is small, but the bias is high. So the bias is driving the test error. So now let's look at p equal to 1 first. In this case, between p equal to 1 and 2, we don't have a closed form solution anymore. So the techniques that we'll use are essentially based on localized uniform convergence and CGMT, Gaussian min-max theorems, etc. Okay, so first for p equal to 1, a lot of you are familiar. If you have sparsity, then we know that encouraging a small L1 norm is going to help. Right, so matching strong inductive bias is small L1 norm. For noiseless case, basis pursuit, which is min L1 norm interpolation, gets you perfect recovery for an n of the order of S log d. But once you have noise, people usually look at the lasso, which is adding the regularization term with lambda non-zero, and then for the optimal lambda, you can get a minimax optimal rate. Okay, this is the story everybody knows. And so our question is now, what if we use basis pursuit on noisy data? So basically this combination, how much does basis pursuit suffer when it's forced to fit noise? So one question is, can we get consistency? And if yes, what's the rate? Okay, so this question has been lurking in the literature. There's essentially there's a gap between two kinds of results. So the first lower bound by Muthukumar et al. Was a lower bound that was saying it should be the lower bound is of the order sigma squared over log d over n. So if d is of the order n to the beta, essentially is a sigma squared over log n rate. So it should be consistent, whereas other works that have focused on adversarial noise, meaning the noise is adversarial, but it's consistent if it decreases with n, if the norm decreases with n. These kinds of results have basically conjectured that the upper bound should be constant. So for adversarial noise, their bounds are optimal, but the question is whether their bounds are also optimal for IID noise. So what we basically showed is that the lower bound was correct, so we could close the gap and actually get precise bounds even up to the leading constant factor. So we get the estimation error rate with high probability that is equal to sigma squared over log d over n. So we have a 1 over log n rate, essentially. Okay, the proof is based on some previous work by Köhler et al. Their results couldn't show consistency, but if we use some more tight analysis, we could get this result. Okay, so here's just a few remarks. So for one, we could only show it for Gaussians, but actually it holds for more distributions. We just don't know how to show it for beyond Gaussians. You could see exactly the 1 over log d over n rate for all the other distributions as well, like log normal and Rademacher. Okay. So as I said, we have a 1 over log n rate. We do have consistency, but we are far from harmless interpolation, right? Because we know that if we use the penalized version plus lambda L1 norm, we could get a S log n over n rate compared to 1 over log n. That's definitely not harmless. And that is because, as I mentioned in the beginning, it's because the variance is too large. Okay, so this is the picture now. So we've seen that we don't have consistency for p equal to 2, but for p equal to 1, we have a very slow rate, and we are still not generalizing well in the sense of compared to what we could achieve without interpolation. And here, the problem is the variance, whereas for p equal to 2, the problem was the bias. Okay, so we don't have harmless interpolation. There we have harmless interpolation, but bad generalization. Still. So for both cases, we're not happy. So the question is, let me just maybe skip this. So the question is now, can we get better rates in between? Since there seems to be a trade-off, there should be something like a U-curve again. And so if there's a U-curve, what is the best rate we can achieve? And how close do we get to the minimax optimal rate if we vary p in between 1 and 2? Okay, so here is just how I will present our results for p in between. So we use this kind of plot. On the x-axis, we have this beta, which is reflecting how much we're over-parameterizing. So beta equal to 1 is d of the order n, and otherwise is d of the order n to the 2 and 3, etc. Right? So the higher beta, the more over-parameterization we have. And on the left side, we have the rate exponent. Right? So we can get results if we plug in d of the order n to the beta into our theoretical bounds, which are quite complicated, so I'm not going to show them. But we can compute this rate exponent alpha. And this alpha will be non-zero and be actually smaller than 0, otherwise would it show this? And so for alpha equal to -1, this is equal to rate 1 over n, so that's really what this minimax rate optimal. And for alpha equal to 0, that's what we got with the interpolators for p equal to 1 and 2. So here it's up to log factors. So basically this 1 over log n term, we just say it's of the order 1 because we don't, like log n is too slow for us. So we're just ignoring log factors here when I write this alpha. Okay, the question is how close can we get to alpha equal to -1 for p in between 1 and 2 in this graph? Okay, so here's the graph now populated with our rates. So we can get order matching upper and lower bounds. And so how the bounds are, like, these are theoretical plots. These points are theoretical. And so what does this tell us? So let's just fix a beta, just fix over-parameterization, and then vary p. What you can see is if you start with p equal to 1, you're at alpha equal to 0. But once you add a little bit, so p is 1.01, you immediately drop to a rate that's really close to the minimax optimal rate. And now if you increase p again, then you get closer to p equal to 2, so you go back to this constant, inconsistent regime. And so if you look at beta equal to or close to 2, the rates can get arbitrarily close to 1 over n. And for classification, you can actually get it precisely. To get 1 over n precisely. Okay. So these are essentially, this is the illustration of our bounds when we plug in n to the beta for d. So our bounds are general for d and n, but I just plugged it in for illustration purposes. So what do we see in this plot? So from one, we also see this second descent, meaning after the interpolation threshold, the rates get better, generalization gets better, the test error drops. So this is essentially, this test error drops kind of equivalent in terms of rates. And then we have harmless interpolation in the sense that we get very close to the minimax optimal rate, and also good generalization because we're close to the minimax optimal rate. So basically, adding a regularization is not going to help that much anymore if we choose a good p in between 1 and 2. So there are some caveats to our analysis. For one, I already said it only holds for Gaussians, and so that is a little bit disturbing because it does seem to hold more generally, we just cannot prove it. And yeah, we've been trying, but so because we crucially rely on the Gaussian min-max theorem, we're not able to show it in a different way. One caveat that also is the reason why we couldn't show experiments is that we require D to be really, really large, which is then hard to actually implement. So for example, P equal to 1.01, D needs to be basically, 1 over log D needs to be 0.01. So D has to be really large to see these phenomena. Okay, so this is why we require this is because we need, in the analysis, we need to concentrate the LQ norm of Gaussians, and to get a high probability result, this is necessary. We don't know how to get around that either. Okay, these are just some technical caveats. Okay, but now on to perhaps some experiments. These are experiments for classification, since the classification results are a little bit more benign in the sense of how large the D needs to be. So here we just have a very synthetic experiment with isotropic Gaussians and a sparse ground truth, linear. And what we see here is following, it's important to take away also for the second part. So first focus on the blue line. The blue line is when we have noiseless data. So for noiseless data, you have a sparse ground truth. Of course, you want to choose P equal to 1, right? So you want to enforce sparsity. Noiseless data always use the strongest inductive bias. So there's a big drop in terms of error between P equal to 2 and P equal to 1. So now if you add noise, which is the orange curve and the gray curve, sigma is the noise level, this is random label flips. In this case, you don't want to choose P equal to 1 here, but you want to go a little bit towards 2 to reduce the variance. And so the best point is going to be here somewhere close to 1.15 or something. So this is for synthetic data. And so we did an experiment also on a high-dimensional data set on leukemia data. And there, the same kind of trend can be observed. So the blue line is if we don't add artificial noise. So it could be that's already noisy, but you know, we get pretty good accuracy, so maybe it's fine. So we just assume that this blue curve is some sort of proxy for noiseless data. So in this case, you also want to choose P equal to 1, the strongest inductive bias. So now if you add a little bit of artificial noise, the optimum of P is again shifting towards 2. Okay, so basically one takeaway from our theory, another way to think about the bias-variance trade-off is that the strongest inductive bias is best for interpolating noiseless data, but medium inductive bias is best to interpolate noisy data. So you'll have these two kind of curves where the optimum shifts towards a weaker inductive bias. Now, I need to add that this is not a kind of constructive or methodological analysis or research, right? So we're not saying, please interpolate and please choose this kind of inductive bias, but we are saying, if interpolation ends up working, if you get an interpolator that generalizes well and you have very noisy data, it could be that it has kind of a medium inductive bias towards the simple structure of your ground truth. So this way around is how we would sell our result. So it's not saying you should use this method. Okay, so what's the full picture for the linear models for P in between 1 and 2? So for one, what I just said, use the strongest bias for noiseless and medium bias for noisy. And the other one was this more kind of bias-variance trade-off idea. And basically saying you kind of have harmless interpolation and not for the strongest inductive bias, but if you have some sort of medium inductive bias. So these two, A and B, these two conclusions, we will want to transfer also to nonlinear models. So for this, we need to, of course, discuss what is structure and what is strong inductive bias, and we'll do this now. Okay, so the first part will be on filter size of convolutional models, of convolutional kernels, and we show some theoretical results, and then we'll go to neural networks. So what are convolutional kernels? You can just consider for each x, so your covariate x that's d-dimensional, you look at patches of size q, right? So you have a d-dimensional vector, you look at patches that are q-dimensional, and you have d of them. And now your convolutional kernel is essentially dependent on inner products of the patches between the one covariate vector and another one, right? So k of xz is going to be a average of some function on the inner product of these patches. So the q is the filter size here, and the kappa here that we allow needs to have some regularity, and that is satisfied by the exponential function, for example. Now for high-dimensional kernel learning, so we look at the regime where d is growing with n, and d and n grow together. And so here again, actually it's quite hard to analyze. So most works are focused on this kind of distribution, which is kind of uniform on this hypercube kind of thing, where you only look at the vertices, -1, 1 to the power of d. So that is maybe not so satisfying. We conjectured that you can also get these results that I show you for uniform distribution of the sphere for a very particular kernel. Because for these, essentially, you can write down the eigenvalues, or you have a very tight characterization of the eigenvalues. And generally, this is not the case, and that's also one of the reasons why people have analyzed this particular distribution. So for high-dimensional kerneling where d is growing, it's actually pretty hard to have a very tight characterization of the eigenvalues for general distributions. And okay, but for this kind of toy model with Gaussian noise, and for a ground truth that has a small, essentially only depends non-linearly on a small patch, we can try to see if these two conclusions that we had for linear models also carry over. So now it's important that the ground truth also satisfies the simplicity, right? So before we had the sparsity, and now we use filter size as some sort of proxy for structure. So small filter size, we assume that like essentially you can use a small filter size to learn f star, and hence a strong inductive bias would be an estimator or a kernel method that's based on small q. And then we compare kernels with different q's given a ground truth that only depends on L star coordinates. Okay, so here we are in the high-dimensional regime, which means that n and d grow together. So L is essentially not overprecision. L is essentially how large n is compared to d. Again, here we're not in linear regime. We're over-parameterized anyway because we look at kernels. So here this L is had nothing to do with over-parameterization. Then we have L sigma. This could be 0 if you have constant noise. So it's just more general. And then gamma is important because gamma is reflecting how strong your inductive bias is, right? So if gamma is small, this means you have a strong inductive bias towards small filter size. Strong inductive bias towards small filter size, yeah. Okay, so what we compare, so we want to see if harmless interpolation happens for a weak inductive bias, and if basically what we saw before, a strong inductive bias prevents harmless interpolation, right? So we need to compare regularized estimators, or ridge regularized estimators, KRR estimators with the interpolators, mid-norm interpolators in the RKHS. So that's what we do, and so the result looks kind of complicated, but I just want to throw it out. You don't need to parse. And what I'll show is actually just the graphical version of it. So our bounds are tight again, and this is important to make the statement that there is a trade-off, and You know, otherwise it's just, if it's just an upper bound, you cannot actually say that much. So they are tight. And what we see here, first of all, is the result for the interpolator, which is this wiggly line on the blue line. And if you're familiar with the literature, you might be reminded of a paper by Liang, Rachlin, and Dai, who also showed multiple descent, or showed an upper bound for multiple descent as a function of over-parameterization. So here, on the x-axis, they actually had d over n. And they also saw some multiple descent. And so that is because of, well, very high level, it's because of the eigenvalue structure. As d grows, you will essentially have this sort of staircase structure, and that's what causes these wiggles. At the same time, if you disregard the wiggles, you'll see a trend that's going down. Right? So the interpolator is somewhat getting a better rates, at least the minimas are getting better rates. And at some point, it matches the regularized, the optimally regularized estimator. So this is the yellow line here. So this is the KRR with the optimal chosen lambda. That is the rate that you get. Again, this is the rate is n to the minus alpha, n to the alpha, and alpha is between 1/2 and 0, or minus 1/2 and 0. So this should be n to the alpha here. Okay. But, okay, so just disregarding the wiggles, right? So if you just look at the high-level curve here, this blue line here and the yellow one, you can see again, for large gamma because if Q is of the order D, you essentially don't have any real filter size. You just use the entire covariate vector in your kernel, so you essentially don't have that much of structure. In the case of very weak inductive bias, you have harmless interpolation, whereas when you have strong inductive bias, using a small filter size, you have a big gap between optimal regularized and interpolating estimator. So we see the same thing, and the reason is also a bit similar, that as you increase the inductive bias, i.e. the smaller the filter size gets, the variance grows, as we saw in the p equal to 1 case. So p equal to 1 was here, and the variance was growing, and the bias was decreasing. Okay, then there was another result that I just added yesterday because of Misha's talk. We can also show that for, is this the right way around? Yes. For weak inductive bias, that fitting noise is actually necessary, and not just that it doesn't hurt. So in order to present this result, we need to define a couple of things. So first of all, lambda star is the optimal lambda for your KRR to get the optimal risk bound for a given choice of L, sigma, the noise, N, and the filter size. You have this optimal lambda star. And then gamma star is basically separating this plot into weak inductive bias and strong inductive bias. So if you're on the right-hand side, so if gamma is bigger than gamma star, then you're in the weak inductive bias side. Okay, so the theorem then says that the training error, the expected training error in probability, converges to some tau times sigma squared. And if I'm in the strong inductive bias regime, this tau needs to be 1. And if I'm in the weak inductive bias case, the tau is smaller 1. So the optimally regularized one has to fit noise to a little bit, otherwise it's not the optimal lambda star. Okay, so what tau equals to 1 means that just basically says don't fit my noise to some extent. Right, don't fit my noise means is the same as basically saying ignore the noise and just try to focus on your structure. So that's the usual regularization regime that we are used to, right? So you should not fit noise, just try to circumvent it somehow. Okay, so this is what I already said. And yeah, so this is an experiment on CNNs. I will show later in a couple of slides which particular experiment I mean here. But basically, we saw for a particular kind of CNN and image data that this exactly happens. is that if your filter size is very large, then you will need to fit the noisy subset of the training set, because it's synthetic, so we can actually define noise, like noisy labels and non-noisy labels. We know this in advance. So the training error on the noisy subset has to be 0, which means we have to perfectly fit noisy data. But if you go into the regime where you have a strong inductive bias, you really should ignore the noise. Right, so this because the training error on the subset being 100% means that I have not fit the noisy data points at all. Okay, so what is this CNN and image data set that I was showing? Well, we had some difficulty trying to think about a controlled experiment that really captures our intuition. And so we were thinking of essentially some sort of synthetic data sets where we know that the ground truth only depends on very few pixels, and so the filter size required is really small. And so here we have circles versus crosses on some images. And the neural network we use is really a very simple one-layer convolutional network. But for this one, so in order to see any kind of phenomenon that is transferring from our intuition in the linear case, you really need to be careful there, because it really hinged on the fact that the ground truth had a particular structure. And so that's wasn't clear to us that any natural image would have that particular structure of small filter size being the optimal estimator. So that's why we had to use this synthetic data set. And so on this one, we could actually see as well on this nonlinear model that, first of all, if you don't have noise, then always use the smallest filter size. And once you add artificial noise, 20%, then the interpolator needs to, basically, you should use a filter size that's in between the smallest one, 5, and the largest one. So you go towards a larger filter size. And also, the other thing is that there is no harmless interpolation for strong inductive bias, and there is harmless interpolation for weak inductive bias, which is large filter size. Okay, so beyond filter size, we're thinking, okay, how can we go to a bit more natural images? Because the synthetic circles and crosses was a little bit unsatisfying. So we're thinking about maybe rotational invariance could also be a structure that is interesting or natural in image data sets. So what kind of images should be completely, okay, so for which kind of image data sets should the optimal classifier be invariant to rotations? And so we thought that this kind of data set called Eurosat, satellite images, should definitely be in that category in particular. So there, the task is given some picture of the satellite image. You have to label whether it's a residential area or agriculture, etc. So these are the labels, and so it really shouldn't matter what your orientation is in order to label a satellite image in this way. And so now the question became, okay, this should be a structural simplicity that makes sense for images, but how do we vary the strength of inductive bias? Right, because we do not have like a particular optimization algorithm that gives us an interpolator that is, has some sort of invariance. It's not an implicit bias kind of result. It's not like a min-norm thing as in the linear case and in the kernel case. It's not that easy. So how we thought about varying the strength is via the amount of data augmentation. So the number of rotations that we add to the regularizer, or the consistency regularizer, essentially. Right, so for each image, we would add k, I think, or number of rotated versions of the same image, and say, please also predict the same label on these rotated images. And that's the number of rotations that we add, or the more like how fine the grid is our strength of inductive bias. This is the best we could think of, but very happy to hear if anybody else is more interesting or even more practical ideas here. And again, for this rotational variant experiment, we see the same thing, which is the number of rotations. As I mentioned, if we have a lot of rotations, we have a strong inductive bias towards rotational variance. And if we only, so for rotation equal to 1 is just the original image. And then we see if, in the noiseless case, you really want to use, for the interpolator, as many rotations as possible. But once you add noise, so I'm comparing this one, the interpolator, right? So the dashed blue line is best for the optimum, the largest number of rotations. But once you add noise, then you want to move towards fewer rotations. And this has been observed previously before. Once you add data augmentation and you have noise, then you should not interpolate anymore, and you should already stop. And there's actually a big gap. Oh, okay. Okay. This is a problem. So, yeah. This was basically also what I had, but are there any questions maybe in the meantime? Okay, so since they're not, I'll continue. Just a recap, right? So we started with the linear models. We had these two conclusions from theory and also in experiments. Then we went to kernels. We had the same for a structure that is filter size and another, and also these two observations for another structure that is rotational variance. So of course these are only, preliminary results. I wouldn't say this claim is very general, but this seems to be one possible ingredient in trying to understand, when interpolation works for noisy data. So this kind of structural bias perspective. Okay, so this is just a summary of the story. So the main takeaway is that we have this inverse bias-variance trade-off as a function of the strength of the inductive bias when we are forced to fit noise. So when the training error is forced to stay at 0. Then in this case, the strongest inductive bias is good for noiseless data, but then for noisy data, you would want to be in the middle to have a medium inductive bias. And so here are still some open questions. So as I already mentioned, we only can show it for Gaussians, and it's very difficult to go beyond. For nonlinear, of course, how do you, again, go beyond toy distributions on the kernel, like -1, uniform distribution -1 to the power of d is kind of toy. How do you go beyond? And then the other question, of course, is neural networks. Can you prove something about those? But the experts are in the audience. And I'm personally also very interested if you have any other ideas how to test the hypothesis that we postulated for the linear case and then tested for a couple of structures. What kind of structures could also be interesting to try our hypothesis on for neural networks or for anything else? Maybe also graph neural networks, maybe some other kinds of structures. So this is, these two papers are the ones I primarily talked about. And these are the L1 results, and these are the structural bias results. So so now I want to thank you, everybody, for staying until so late in the last talk, and again, for the organizers for this wonderful workshop.
Thank you, Fanny, for the great talk. Are there any questions from the audience?
Very nice talk. I have a question about this. So you said that the lower bound, there was optimally regularized predictor whose training loss was below the noise level, right? Can you say a little bit more about that?
Yeah, that slide was for you. No, that's too fast. For the kernels, yeah, why am I going to the linear ones? For the kernels. Yeah, so we have results for every lambda. So for every lambda, we can show, we get tight bounds for the regularized estimator. Here. So for every L lambda, which is the order of the lambda as a function of D, we can get tight risk bounds, and then we just kind of take the lambda that minimizes the sum of both. And so that's our lambda star, right? So because the bounds for every lambda are tight, that's why you can get this necessity, essentially.
And how much lower than the noise level it is?
Yeah, that's a very complicated expression, this tau gamma.
But can you say it's like 0.5 the noise level or something? Can you get some separation from 1?
Yeah, but I'm not entirely sure. We didn't numerically calculate it. But
All right. Thanks, very nice.
Thanks.
You showed that changing the inductive bias, changing the inductive bias, you find that with noisy inputs, noisy data set, you get better results with less inductive bias. So is that, do you think that works in reverse order? Like you could find if there is noise in data by changing the inductive bias.
Can you repeat the last sentence?
Okay, so can you find if there is a noise in the data by changing the inductive bias?
I see. That's an interesting question. Yeah, well, we don't have the theoretical results, but experiments kind of show. But you're basically saying, okay, you could vary the inductive bias, and if the strongest one is the best, then maybe that means that you don't have noise. Yeah, maybe you can try experimentally, but yeah, it's not a theoretical result.
Yeah, thank you.
Thanks, that's a very interesting talk. You said just for the linear case, you had the P between 1 and 2. Do you have a specific model where you get P between 1 and 2 as an implicit bias? Because I know like P equals 1 and 2 you can get in linear diagonal models, but is there...
You mean like implicit bias, whether you get...
P between 1 and 2,
no, we just looked at the actual like the optimal solution. We didn't look at the optimization procedure towards that.
Okay, just I want to say, because the model I showed in my talk, the last part, in linear diagonal models, you actually get P between 1 and 2. So if you get, like for depth 2, you get P equals 1, and as depth goes to infinity, you go to 2.
Okay, yeah, nice.
So that may be a case that could be useful to check.
Yeah, thanks.